Hello and welcome back to Nunley Math. I'm your host, Aaron Nunley. Thank you so much for joining us as we work our way through Algebra 1. Specifically, we are looking at graphing functions, or as I like to say, putting the fun back into functions. In our last session, we talked very quickly about linear functions and how we were using linear functions as a model for how we want to begin to think about functions and how we want to begin looking at patterns that exist within functions. I'm not going to review that information because I'm hoping you've already watched that video. If you haven't, I would suggest you go back and take a look at that video before proceeding to this one, as I find it will be very, very helpful to you. One of the most important things we talked about in the previous video is this idea that there are function families or certain types of functions that have a lot in common. They have some common characteristics, and that by knowing those characteristics, we can begin to work more quickly and easily with functions. We talked about the fact that the way we're solving functions in this first set of videos is not the most efficient way. In fact, it's probably the least efficient way that we can work with functions, but it is very helpful to us to at least walk through this process one time because it allows certain patterns to emerge. And once those patterns begin to emerge, we can begin to do these in a much easier or faster way. So here's what I'm going to do today. We have a new function today. F of x equals the absolute value of x. F of x equals the absolute value of x. Just like in our last video, I'm going to be choosing values for my domain that I'm going to test out in my function, and they are going to hopefully give me some range values that I can list as coordinates and then graph those on the coordinate plane. If I do those correctly, hopefully some kinds of patterns will emerge that we can use that will be very, very helpful to us. So that hopefully after we do this the long way the first time, the next time we do this it'll be a little bit faster, a little bit easier for us. I would strongly recommend that prior to watching this video, you take your own graph paper and your own tables and that you begin to You try doing this, plugging in points on your own. I'm going to do it relatively quickly here, so you might have trouble keeping up. I'm going to operate under the assumption that most of you are pretty good at just plugging in numbers and simplifying. So I always try and start with some easy numbers. So I plug in a 0 for my x. F of 0 equals the absolute value of 0, which is 0, 0. And I graph that on the coordinate plane. Again, if graphing coordinates is difficult for you, this is probably not the video you want to start with. You probably want to go back and pick that up before beginning this lesson. I'm going to plug in a 1. I'm not going to write f of 1 because that's going to become tedious. It's not really our focus today. But I get 1, 1. I plug in a 2. Absolute value of 2 is 2. I get the point 2, 2. I plug in a 3. The absolute value of 3 is 3. And I get a point here. Now, I'm thinking I'm beginning to see a pattern. I want to check and see if my pattern is correct. So I'm going to try something a little farther away just to make sure. The absolute value of 8, maybe, would give me 8, 8. And this does match what I'm thinking the pattern is. Hopefully you can see the pattern as well as you are working on this. It is always a good idea to go ahead and try a couple negative points as well, just to make sure that nothing weird happens in your pattern. So for example, I might use a negative 1. The absolute value of negative 1 is positive 1. And oh, this has done something different. Instead of continuing down like it looked as though it would, it comes back up. I find that interesting. Negative 2 gives me a 2, and I'm here. I call that my ballerina with a bad attitude point, negative 2, 2. It also amuses me that it's on point, but that's only funny if you're a dancer. Negative 3, the absolute value of negative 3 is 3. So if I graph negative 3, 3, once again, I think I found a pattern. I'm going to go ahead and pick another point as well. Maybe I'll pick a 10, a negative 10. Negative 10, and I get positive 10, and so I graph that. Again, if you fell behind in your plotting of points, now's a great time to stop your video. Get those points plotted before restarting. As I look at this, I'm beginning to see that a pattern has emerged. It is different from my last function, my linear function, because it does not make a straight line. Any idea what this one seems to do? to me, it appears that this is making a V shape. A V shape. That looks kind of like this. And I can test that out by plugging in other points. 5, 5 works, 6, 6 works, -7, +7 works. Every point that's on this line will work. If I put in a 1/2, I get a 1/2. If I put in a -3.5, I get a positive. Every point on this line seems to be working. And in fact, this shape is a very, very common shape for us when we have functions. In fact, this type of function right here, with the absolute value sign around the x, is known as an absolute value function. An absolute value function. And the graphs of this type of function are always going to form that basic V shape. Now, I will tell you, some of these V's will be like we've seen them. Other V's will be really, really wide. You might have some tall, skinny V's. You might have upside down V's. But every absolute value function is going to make a V. And they're pretty easy to spot because your x is inside of absolute value bars. A couple things I want to make mention of. This point right here, the point 0, 0, is the point where our graph changes what direction it's moving. As I read from left to right, I'm coming down, 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 until I hit the point 0, 0. At the point 0, 0, the graph turns and starts coming back up. Because this is where my graph changes its direction or changes what it's doing, this is known as a vertex. A vertex. It's where the graph changes what it's doing. And try not to be too formal on that, because I want it to be really clear what that means. The graph changes what it's doing. And in fact, this particular vertex happens to fall on the origin. Notice the origin is that coordinate 0, 0. It's the point where your x and y axis meet. That means that your x-intercept and your y-intercept are both that point 0, 0. It crosses the x-axis at 0, 0. It crosses the y-axis at 0, 0. I also have a third name, or I guess you could say a fourth name for this point. Since it is the lowest value that f of x can have, or the lowest point in my graph as I read it up and down, we also call this a minimum. A minimum, the lowest value that our graph will ever have. Now, it is important to note that depending on what happens with our v, whether it's wide or skinny, whether it's upside down or right side up, it can also move right, left, up, down, diagonally. This V can move all kinds of different places around the coordinate plane based on some of the properties and principles we're going to learn over the next couple of weeks. But it is important to know that it will always have a minimum if it's upright, and if it's upside down, it will always have a maximum. There's a lot of value for us in finding where that minimum and maximum are located. It can save us a lot of trouble. One last thing I want to make sure I point out before we talk about the domain and range, and that is this. Absolute value functions always have a line of symmetry that passes through the vertex. A line of symmetry that passes through the vertex. Remember, a line of symmetry just means that if I were to fold my paper along that line, all the things on the right side would line up with the things on the left side. So if you look here, this point 1, 1 is one space away from that line of symmetry. The point -1, 1 is also one space. They're mirror images or reflections of one another. These 2 points are each 2 spaces away, 3 spaces away. If you come up here, you can see that this is 7, 8 spaces away from the line of symmetry. If I were to go 8 spaces over here, I get an extra point. Same thing here. This is 10 spaces away. This would be 10 spaces away. I point that out for two reasons. Number one, knowing the line of symmetry can save you a lot of trouble, because if I begin the problem knowing ahead of time its absolute value and knowing ahead of time that the graph is going to be a V, if I can find that line of symmetry, I only need to graph one side, because I can take that, flip it over to the other side, and get all the other points for free. It literally cuts your work in half. This line of symmetry is a vertical line. Vertical lines are always named by the spot on the x-axis they cross over. So this line of symmetry is at x equals 0. X equals 0. Notice this is 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, 5. All the x part of the coordinates are all zeros. Last thing, domain and range. Domain is what values I can put in. Every value I stuck into this function gave me an output value. Notice that my arrows say that as I'm going to the left, we expect the pattern to continue. As I go to the right, we expect the pattern to continue. So my domain here, I'll switch back to my blue pen, is every value of x should work as long as x is on the number line or is a real number. When I look at my f of x or my y, remember that's my range. I'm looking purely at where this goes up and down. When I'm looking at my output values, I notice that as my x's get smaller, my y's get bigger, or my f of x's get bigger. As my x values get closer to 0, my y values are going down. Then they reach 0, and as they start going from 0 up in a positive direction, my y values start going back up. I always read my graph from left to right. So it comes from up here in infinity, down to 0, then it turns around and comes back up. Because of that, my range is only those numbers that are greater than or equal to 0. I can stick in any value I want. That's what the domain says. But no matter what I stick in, it is impossible for me to get a value smaller than 0. That's because if I put a negative number in here, the absolute value makes it come out as a positive. If I stick a 0 in here, the absolute value comes out as a 0. If I stick a positive in here, the absolute value comes out as a positive. No matter what I stick in this absolute value function, it's never going to give me a negative number. Now, some absolute value functions will, and that's going to move their graph around in order to make that happen. But in this case, our range is set. Hopefully that has been useful to you. Again, this is not the best or most efficient way to graph an absolute value function. This is probably the worst or least efficient way to graph an absolute value function. But it did reveal for us some patterns that the next time we see this will make it much, much easier. After we've gone through all 7 different types, we will go back and look at those again. Thank you again for watching. Hopefully this has been useful to you. Next up, we're going to talk about functions that look like this. I hope you can join us for that. If this has been helpful or useful to you, please take a moment and leave us a comment in the comment section. Make sure you like and subscribe and turn on your notifications so that you don't miss any of this as we work our way through Algebra 1. Thank you so much. Take care.